dici? La luce la abbassiamo un po', si riesce? Almeno.
It's
I think
better,
a little
the
bit,
lights.
at least this part. They're all together.
Ah,
Okay.
yeah, you tell me.
I thought it was better to have a bit the lighter off, but as you like.
Good, okay, let's start. 11:15 exactly, okay. Good, very happy today. So we're doing a joint seminar. Last one we did was in July, so this joint astro and high energy physics. And we have the pleasure today of having Ilia Musco. So Ilia did his PhD at CISA, Trieste. Now I have to read a bit of a list. And then he held positions in London, Oslo, Paris, Barcelona, Geneva, and Rome. And now,
traveling.
Yeah, he likes traveling almost as much as Sasha. And, right now he's a SMASH fellow at the University of Nova Gorica, so it's quite close to us.
Very recently, just started this year.
Good. And he's going to tell us about primordial black holes. Please.
Thank you, Lorenzo. Thank you also, Janez and Dunia, for the invitation. They're organizing this seminar. Very surprised to see this big audience, so quite scary. So from what I've been told, the audience is a bit mixed, astro, high energy. So I suppose that you are not particularly experts on primordial black hole. Maybe you have heard about. So I will start very, very simple with a bit of history also. And so please interrupt me to any time if you have questions. So first of all, I've been working on primordial black hole since I started on my PhD already. Actually, I was a master's student when I really got interested in 20 years ago on primordial black holes. And then I did my PhD working on that, also during my first postdoc. And then I wanted to change a little bit topic, also because I have to say that this topic was a very, very narrow until 10 years ago. Almost no one was interested in the topic, apart from a few people in the world. And then as it happens, things change, because after the detection of gravitational waves in 2016, I was in Paris at that time, and people started to get very interested about it because primordial black hole became one of the potential candidates for dark matter. And there was some paper claiming that some of the signals coming from LIGO, Virgo, Cagra, or gravitational waves from mergers of black hole could be of primordial origin. And I will say something about that later in my talk because I did some work on that. So as it happens, I was forced to continue working on the topic, even if I did also something else, but I really I have to live all my life with primordial black holes. So primordial black holes actually was discovered since quite some time ago. It was an idea that although it was not called primordial black holes, I have to remove the volume. Although it was not called primordial black hole yet, but Zeldovich and Novikov, because I guess you know these very famous names in Russia, at the time of the Soviet Union, they start to argue about something which was basically that, although they didn't call it. So the idea of having some very compact object in the very early universe. So they argued about, but in their calculation, which actually was wrong, because it was not taking into account relativistic effect and so on, they were arguing that if some kind of very compact objects would form in the very early universe, they argued that the universe was a kind of collapse into these objects, so that was not possible to have it. Please, welcome. And then later on, Stephen Hawking came out with a very simple paper published on the Royal Astronomical, monthly notice of the Royal Astronomical Society, really putting this idea in a more clear framework, calling it as primordial black hole. So Stephen was said that if you have a very cosmological perturbation in the very early universe, which is what we expect to have, a spectrum of cosmological perturbation giving rise to the structure we see. And if the length scale of this perturbation is small enough to start to collapse when the perturbation is still radiation dominated, so relativistic, what Stephen Hawking argues that with such an equation of state, which is what characterizes a radiation-dominated universe, the only thing that you can form is it's a black hole if you overcome the pressure gradients that tend to prevent the formation of such an object. Otherwise, you just disperse. which is actually what exactly happens. And the reason is because when you have an equation of state simple like that with 1 degree of freedom, because in this equation of state, the rest mass density is 0 because it's negligible, and then you just have a kinetic component. If you don't have a rest mass density, what you get in a gravitational collapse is that you cannot virialize. So or you overcome the pressure gradients and you form a black hole, otherwise the perturbation just bounce and disperse. And this is a fundamental thing in gravitational collapse. And so Stephen Hawking argued that could be a possibility, so the very first object you can form in the early universe is a black hole if you have a perturbation large enough in terms of amplitude. And the interesting thing about this idea of Stephen Hawking was, if you can see the date, it's 1971 when he published the paper. But Stephen Hawking is very famous for his very discovery about black hole evaporation, which came out in 1974, combining quantum mechanics in a semi-classical calculation with general relativity, and discovering that black holes are not so black, but they have a thermal spectrum with the rate of evaporation going like the inverse of the mass. So if smaller they are, quicker they evaporate. But the interesting thing is that the idea of black hole evaporation was triggered to Stephen Hawking by the idea that he had on primordial black holes a few years earlier, because if you make a simple, using the Schwarzschild length, you compute the typical size of a black hole with respect to the mass, you see that if you have a mass which is small enough, like what you can form in the early universe, because the typical mass of primordial black hole is the mass of the cosmological horizon at horizon crossing. So earlier you go in the formation, in the time of the universe, smaller are the typical primordial black hole that you form. Then if in the very early universe, you can form a primordial black hole smallest particle, because you don't have the Chandrasekhar limit like for stellar black holes. In primordial black hole, the only limit that you have is the horizon mass. That's the typical size. So it's basically the time of the formation which tells you the typical size and the typical mass. And so the interesting thing to know is that the Hawking evaporation effect was triggered to the idea of primordial black hole that Stephen Hawking had a few years earlier. And what tells this idea is that because the rate of evaporation goes like the inverse of the mass, this tells that if you have a mass 10 to the 15 grams or smaller, the rate of evaporation is smaller than the current age of the universe. So primordial black hole formed with which is mass smaller than this value, which is 10 to the minus 18 solar masses, should be already evaporated by now. So if primordial black hole exists now in the universe, they should have at least this mass of larger. So that's what if you apply Hawking operation. Now there is some new ideas very recently came out, like called memory burden, where there is some idea by Gyat Valley and other people that they are claiming that the Hawking evaporation is not really behaving like that. There is at some point a saturation. It's a quantum effect, making some assumption of a potential theory of quantum gravity. So if this is true, then it's possible to have also smaller masses. But standard scenario, that's what the Hawking evaporation effects tell you.
What is this?
It's called memory burden. It's just an idea that basically it's a saturation of information, and so that at some point this tells you that you cannot, you saturate, you cannot keep evaporation. So the evaporation goes for some time and then saturates and then stop. And that's
Why would it stop?
because you cannot, because there is I'm not an expert, to be honest. I know very well a colleague which is working on that. I saw some seminars. But basically, there is a saturation of information that you cannot be lost, basically. But there is some assumption in terms of, I mean, it's not going to be my topic. Anyway, I'm just going to tell that there is some new ideas that are suggesting that Hawking operation does not go all the way down to zero mass. I mean, it's not, of course, it's an idea that has been supposed, and it's based on some idea of potential quantum gravity, but we don't know, of course. Anyway, I'm going to be classic anyway. That's the only thing I can say about quantum mechanics. I'm not going to say anything else about quantum mechanics today. I just want to mention this because it's an important aspect of primordial black hole that is also very important historically. Anyway, so primordial black hole forms if the amplitude of perturbation that I will call delta is closer than a particular threshold delta C. Otherwise, if the perturbation has an amplitude which is smaller, they just bounce and disperse. And this is what we really see in the simulations. Bernard Carr, which was Stephen Hawking PhD student in Cambridge at that time, was the first, now he's considered the godfather. Bernard has been working on primordial black holes since ever. Now it's emeritus at Queen Mary College in London. And he was the first person estimating the value of this threshold, computed at horizon crossing, when the perturbation cross the horizon and start to collapse. And the value is, in a very simple argument using Jeans length in Newtonian physics, tells you that the value of the amplitude is of the order of the sound speed square, which is dp over d rho, where sound speed for this equational state is 1/3. So it's order 1. So this tells you that the amplitude of perturbation collapsing primordial black hole are non-linear. So we cannot use, this is something that I stressed from the very beginning, we cannot use standard cosmological perturbation theory to describe primordial black holes. We have to do something more elaborate, which I'm going to show you. The first thing I want to discuss a little bit is the thermal history of the early universe after inflation. So let's suppose we have a mechanism like inflation of anything that produces a spectrum of primordial perturbation. After that, we start with the radiation-dominated universe, which gets colder and colder evolving with time. So in this plot, what I'm plotting is the equational state of the early universe. In particular, what I'm plotting is two quantities, the value of W, which is the ratio between the pressure and the energy density, and the value of sound speed square, dp over d rho. In standard radiation-dominated universe, they are equal 1/3, so it's constant, so there is no intrinsic scale. But in the standard history of thermal history of the universe, there are three epochs where there is a change, and so the equational state has an intrinsic scale, and there is a softening of the equational state. So in this plot here, what I'm plotting is these two quantities against the log of the temperature. So the time goes in this direction. So Big Bang is asymptotically down here. So you get after inflation, you come back here with W equal 1/3, and then you have this little softening, which is the electron weak phase transition. Then the second big softening, which is about 30%, is this one, which is the QCD phase transition, which is quite soon after. So after the electron weak, you get just back to 1/3, and then you start the electron weak, the quark-hadron phase transition. In the quark-hadron phase transition, what you have is that before the minimum, the universe is done of free quarks. After the minimum is done of quarks confined into hadrons. So that's with this little plateau, and then back to standard radiation-dominated universe, and then back to a third softening, which is the primordial nucleosynthesis. So all this plot is describing the thermal history of the early universe when we are still in general radiation-dominated, before equivalent, before CMB. But I want to stress that there are three softening where the pressure gradients in particular are naturally smaller, and because the threshold, as I showed you, as order of magnitude goes like the pressure gradients, we expect that the pressure for primordial black hole in these three epochs is going to be smaller. And if the threshold is smaller, it's clear that the possibility of forming such object is larger. So there are three epochs, in particular the QCD, where there is a natural enhancement of primordial black hole formation. And the interesting thing that is to look at a typical scale of primordial black hole in these epochs. This one is typical scale of asteroidal planetary mass, which is one of the candidates for dark matter. This scale here, in particular around this, the minimum is around the solar mass. So in particular, the minimum is around 2 solar masses. So which is the typical scale for binary mergers of signal between LIGO Virgo. All the QCD goes from 0.1 to 100 solar masses. So it's perfect range for LBK signals. And the third softening during the primordial nucleosynthesis is 10 to the 3, 10 to the 4 solar masses, which is exactly what you would like to have for the seeds of supermassive black hole that we observe in the active galactic nuclei. As you know, there are some AGN that now are observed with a very large redshift, like almost 10, and it's very difficult to explain how they form astrophysically from collapse of population 3 stars, because these are formed very early and there is not enough time to have a super-Eddington accretion. It's not so easy anyway. Also, primordial black hole has some problem, but at least if primordial black hole are formed with enough abundance in this epoch where there is a softening, you could claim that then they can accrete, they have enough time to accrete. The things is a bit more complicated, but at least, so just to want to point out in a simple way that there are 3 epochs in the early universe where primordial black holes are naturally enhanced, and exactly in the 3 mass range where we can have interesting candidates for 2 different completely channels of formation, dark matter candidates, LVK gravitational wave signals, 6 supermassive black hole. 3 completely different scale of objects which are very interesting for explaining what we observe in the early universe today. Please.
Question. So this is based on the previous slide. You had this genes. This is just genes instability.
No, this is just a question of state.
No, on the previous slide. Why one argues that you need this, that the enhancement comes when essentially the speed of sound is lower.
Because the threshold is related to the pressure gradients.
But this is the genes instability.
No, that's an ordinary manual calculation which the numerical simulation confirm. The genes.
The numerics. So they do numerics and that. Okay.
I do the numerics.
Oh, you do numerics.
Yes.
And
I will show you.
This is relativistic.
The numerics, of course, tells you things more precisely, which I will show you. The genes argument tells you things as order of magnitude, give you just a simple estimation in terms of order of magnitude. Then the numerics tell you more precisely how it works. But the physics is pressure gradients.
So I was going to ask, so the genes argument works for something that's close to radiation? Because normally when you solve it, you assume...
Okay, there is a paper done by Tomohiro Arada, which was a postdoc with Bernard in London. I met him at that time, which is really generalized the genes argument in relativistic physics, and you get a small correction of about 20%. So if you do apply generativity to genes analysis, you do genes argument in generativity, you get the same order of magnitude estimation with for example, instead of 1/3 gets 0.4.
No, that's okay. I mean,
It's a 30% correction.
So my question is, does it still work when you're in radiation?
Yeah, sure. Because why should not? Because I mean, what you have, you have a perfect fluid. You have density and pressure. That's what the equation of state has. So the only thing
any equation of state
for any equation of state, for any equation of state like that, which is a perfect fluid without rest mass density, the only thing that can prevent primordial black hole to form is pressure gradients. So larger is the value of the pressure, more difficult to form primordial black hole. If P is 0, anything will collapse into primordial black hole because there is no any pressure preventing the collapse. Of course.
Where's the expansion?
No, because when you have the collapse, the region decouple completely from the expansion. The perturbation expands initially, but then if you have an overdensity at some point this, because of gravity, decouple, and then is what the simulation shows, what I've done, is that completely forget about what happened. You get into a self-similar solution as you would be in vacuum, because you get a really causal decoupling. So the universe at how it continue expanding, while the centers still keep collapsing, and you get a rarefaction larger and larger in the middle, which create basically an almost causal disconnection between the 2 regions.
But in order to decouple, you need to lower W.
No, you need just to overcome, the collapse happens if the perturbation is let's say, nonlinear. Okay. Then if you have above a certain threshold, the collapse gives rise to a black hole. If you are below the threshold, the collapse still happens, but then at a certain point, pressure gradients wins, and then you bounce. But the collapse still happens.
So that's why you need the softening?
No, the softening just reduces the threshold, and so makes the formations easier. But the threshold, for any equation of state, you have a threshold. If it's going to be stiff fluid P equal rho, the threshold will be really order 1, but it still have a threshold. Of course, larger it is, more. The point is that if you plot the probability of delta in terms of delta, what you will have in a very standard, simple argument, you have a Gaussian distribution. It's not really Gaussian because it's a nonlinear. We know that in detail there are intrinsic non-Gaussianity, but let's assume it's a Gaussian distribution for simplicity. The threshold is here. So the perturbation on the tail of the distribution will collapse and form primordial black hole. These others will not, or even this one in the very small will not collapse. There will be a range where they collapse and bounce. But that's what I'm saying. There is a threshold in the tail of distribution which gives a portion of perturbation forming primordial black hole. Smaller is the threshold, larger is the fraction of primordial black hole formed, and so the possibility to have in particular epochs of the universe, a larger abundance.
Yeah. So we get primordial black holes regardless.
Sorry?
We get primordial black holes regardless. So they should be.
In principle, yes. The question is, they are so few that basically they are totally negligible, we'll never observe them, or they are enough that they can really contribute to our universe. That's the question. And of course, that's what I'm going to try to tell you how you can understand that. But in principle, yes.
Maybe you wanted to finish. That's it.
No. But in principle, yes. Primordial. At least I think one primordial black hole in the universe should exist. At least one, probably. I would say.
I have a very great question. So when you say that if you do, so the primordial black holes follow the QCD phase transition.
Yes.
And they have solar masses.
Typical, yeah, typical.
You're talking about the mass today, or?
Yes, solar.
Yes.
I mean, today. I mean, if they have not. No, at the time of formation. At the time of, no.
Form already with the solar
Yes,
mass.
at the time of formation.
So the QCD transition happens.
Yes.
During the QCD transition.
The typical mass, of course, typical mass is solar mass. Well, between 0.1 and 100 solar mass. But the minimum one, the value of the minimum, is 2. Where you will see my plot later. In the minimum, you have a kind of attractor solution where most of the black holes are formed around here. Is around 2 solar masses, because of this 30% softening, with a spread between 0.1 and 100, which is exactly the range that you have supermassive black holes or, that you observe, so the range of black holes merge that you observe in LBK nowadays. Okay? Makes sense what I'm saying so far? Good. So without scaring you, just let me flash. These are, okay, I do the numerical simulation on primordial black hole formation, so I'm a numerical relativist. And in my simulation, the only assumption that to do is we are spherically symmetric. It's a good approximation for primordial black hole, because these are large peaks in terms of amplitude. In peaks theory, larger is a peak, more spherical is going to be. If the peak that is going to be an infinite amplitude is going to be perfectly spherical. And because this is already nonlinear in terms of what we are looking for, spherical symmetry is a good approximation. There are some now recently, we are really starting to do some non-spherical numerical simulations, which are much more demanding in terms of computing time. And what we basically see that the corrections are small, order a few percent. So just this, the indication tells that, I mean, they are interesting to be done anyway for the fact that in spherical symmetry you don't have emission of gravitational waves. What you still have, instead you have beyond spherical symmetry. So for the effect of gravitational wave emission due to primordial wave formation, it's still interesting. But in terms of formation, it's not going to give a big effect. So we can stick with spherical symmetry to understand primordial black hole formation. And in the comoving slicing, which is a more intuitive and simpler slicing of your space-time. So in comoving slicing, you can basically write the metric of your space-time in this diagonal form, where this A is the lapse, B is the 1-1 component, which is related to spatial curvature, and this is the area radius, which is the physical distance from your center of symmetry. And of course, all these quantities now are a function of cosmic time t and comoving radius r. If you are homogeneous and isotropic, this metric reduces to the standard FRW metric, Friedel-Walker. And so if you then couple together relativistic hydrodynamics with the general relativity, that's the set of equations that you derive. So this is the velocity of the fluid. So Einstein equations are second-order differential equation, partial differential equation. So because for a numerical solution, you want to linearize your equation to have a stable numerical solution, what you usually do, you add some additional variables, defining this quantity, which is the proper time derivative of the area radius, which is basically the fluid velocity. In fact, in FRW, this is going to be double law, U equal HR. And this is the gamma factor, which is the proper spatial derivative of the area radius. With these two additional quantity, all your differential equations are first order, and these are the equations that you derive. So this is the Euler equation, basically, where you see this is the gravitational, the Newtonian potential with the correction due to GR. This is the pressure gradient. This is in Newton physics. This is nabla P. This is the continuity equation, this is the energy equation, this is the lapse equation, this is the mass conservation in terms of special gradients at time evolution, the constraint equation. But this system is not closed. To close this system and solve it, you need an additional closure relation. I can ask you which is, of course, if you have done some, what is the closure relation, which of course we need, is the equation of state. So the equation of state is always the closure relation that you need to add to your hadro to gravity system to solve. Without the equation of state, you cannot solve this system. And that you choose because that's the physics. And actually the equation of state specify the kind of object that you form, if you form some virialization, or anything else. So specifying the equation of state, you close the system and you can solve it numerically. One thing that you see in this equation, in spherical symmetry, I wrote this equation in the most general form in a spherically symmetric approximation, which is assuming the possibility that radial pressure and tangential pressure are not equal. So in spherical symmetry, you can have potentially two directions of pressure, the radial one and tangential one. If you are isotropic, of course, they are equal, and then all these terms, PR minus PT, are 0, and they cancel. So in the simpler case, PR equal PT, and so you get some cancellation. But in general, there is some possibility of anisotropic, even in spherical symmetry. Then, how to solve these equations? What you do, you put your initial condition in the slicing of this equation, which is it's quite simple, and you know how to treat it also at a perturbative level initially, as I will show you, to put initial condition, which is given by this dashed line. So you start with this initial dashed line slicing, but the problem of this slicing, the co-moving slicing, is that the observer is co-moving with the fluid. And so you form the apparent horizon, you see the black hole forming, you really see it. But then you cannot compute the final mass, because when you form the apparent horizon, matter from outside is still accreting, and the mass is still growing. And at some point, because the observer is co-moving with the fluid, the observer sees what happens both outside the apparent horizon and inside. And at some point inside, you have the formation of the true singularity, and the curvature singularity, which of course makes the code to stop working. So there are two options. In standard 3D simulation, people do excision or puncture, which is a very refined technique where you basically freeze the central evolution and you keep evolving what is happening outside. And in this way, but you have to do it carefully. It's a numerical trick, which is actually completely consistent. You can do it. But in spherical symmetry, you can profit of the fact that you can do a simpler coordinate transformation, going from what is called the cosmic time, the co-moving slicing, to the null slicing, where your observer is put at the edge of the grid, asymptotically to infinity, and then the formation of the apparent horizon is redshifted at infinity, because if you are outside the black hole forming far away, the formation of the horizon collapse produces an infinite redshift, and then what you see in the numerical simulation that you approach asymptotically the condition for the apparent horizon formation. And that's what exactly I'm doing here in this plot from my earlier. This is my simulation from my very first paper, 20 years ago, when I was still a PhD student. So this condition here is the condition R equal to M. So in spherical symmetry, the condition for a formation of an apparent horizon, it's very simple. It's just the Schwarzschild condition, but now it's a dynamical condition. So in generativity, the apparent horizon for a black hole is a marginally trapped surface, which is basically the outermost trapped surface for outgoing null rays. Make sense? So you basically want to have that. You want to have the outermost trapped surface that prevents anything to go out, and that's basically the definition of a black hole horizon. The difference between Schwarzschild and a general black hole is that in Schwarzschild everything is stationary, so the horizon is stationary, because everything already collapses into the singularity, and everything is vacuum. But the black hole, in a general gravitational collapse, when you do numerical simulation, what you see is that the apparent horizon forms when the matter is still collapsing. And so this is the dynamic. It forms at some point, but then this evolves, so that there is a trapped surface which is expanding because of matter. Actually, if I do are you familiar with Penrose diagrams a little bit? Okay. If I plot the Penrose diagram of Oppenheimer-Snyder, which is the simplest gravitational collapse that I can think of, that's my event horizon, which is traced back from null infinity, from sky plus back. But the horizon, the matter collapse, like that. This is the point when the apparent horizon forms in a time slice in T formation. And then that's the outgoing horizon, and that's the, so in a general collapse, if I plot 2m over r against r in a comoving slicing, what you get is that at some point, this is going to work like that. At some point, you form the horizon, but then this keeps going like that. So you have an outgoing horizon given by this, with the matter accreting and expanding outward, but you also have an ingoing horizon moving inward, which is this one in Oppenheimer-Snyder, which in the end it will annihilate near the singularity. It's a bit more complicated than that, but I will. But anyway, in a general collapse, you form the apparent horizon which split in two trap surface. One moving outward, which is the real apparent horizon of the black hole, preventing anything to go out, and one moving inward. In the end, when the Schwarzschild case is when all the matter is in the singularity and everything is vacuum. So until you reach Schwarzschild, you have to try to track the r equal to m condition. So this is the general condition for the formation of an apparent horizon in spherical symmetry, where either radius is equal to m, where m is the Misne sharp. And the spherical symmetry allows you to have a very clear definition of because in spherical symmetry the mass is very well defined. There is no ambiguity about what is the mass, because there are different definitions of mass, Kodama mass, Misne sharp mass, which are beyond spherical symmetry. They are not coincident, but at least in spherical symmetry there is no ambiguity. So it's very clear how to define the formation of apparent horizon. Another reason to use spherical symmetry if you can. So what you see here in these plots is these are the initial condition dashed line, or when the perturbation is super horizon still expanding with the universe. Then at some point, because it is expanding initially, the maximum is decreasing. Then, because the amplitude is large enough to produce a collapse, then at some point decouple from the expansion, and because this is very close to the threshold, as you can see, delta minus delta c, order 10 to minus 10, you have this very nice self-similar behavior where the maximum moves at nearly constant rate towards the center. So while it collapses, because pressure gradient still acts, you lose matter. So and if you're above the threshold, at some point gravity wins and you go up to 1 and you form the primordial black hole. Instead, if you are below the threshold, at some point the maximum goes down, and this corresponds to the bounce with the dispersion of the perturbation producing compression waves. So that's the only thing that you obtain. The asymptotic solution where this goes down to 0 is the delta equal delta c corresponding to a zero mass black hole, because in fact, because it's there is no intrinsic scale in the problem with such an equation of state when p equal rho over 3, you reproduce exactly the fact that you have a nice scaling law behavior corresponding to the critical collapse mechanism. So where the mass is proportional to delta minus delta c to a power gamma, normalized to mh, where mh is the mass of the cosmological horizon crossing. So mh is just the normalization that tells you the scale order. Delta is the amplitude of perturbation. Delta t is the threshold determined by the equation of state and the initial configuration. And also this k here, this coefficient is given by the initial configuration in the equation of state. While gamma, the exponent, it's an universal exponent which depends just on the equation of state. It's completely independent from the initial configuration of the initial condition, but depends just on the equation of state. For radiation, it's 0.36. And that was this mechanism of critical collapse was discovered by Chotwick and other people in the 90s for very ideal cases of black hole formation, but then in primordial black hole it arises naturally because of the simple equation of state that you have. And actually,
computed this analytically? 0.36?
Yes, you can. Well, that's come from a fit of my numerical.
No, that's not analytically.
It's a semi-analytical. You can do it semi-analytically. There is a paper, Choptut and Nielsen, and there is a semi-analytical way you can compute all this for the yes.
Okay.
Or you do the numerical calculation, you fit it, because these are the dots of my numerical simulation. You do a fit, you get exactly this value, which is consistent. So that's how the mass behaves. But in practice, of course, getting very close to the threshold is you get an extremely large fine-tuning. So I can tell you that if you use peak theory with probability distribution, the typical mass here goes that the most of the masses in terms of probability distribution are between 0.1 and 1 horizon mass. But with a nice scaling behavior so we know exactly the parameters that we have to put, and this expression is useful to when you do the mass distribution for your cosmological scenario. Okay, so let me now explain you how you connect. These are the results, basically numerical simulations. Let me now explain you how you describe the initial condition, because understanding how to describe the initial conditions is crucial to understand then how to connect the cosmological model, so which is basically the power spectrum that you compute from your inflation model, to the possibility of predicting the abundance of primordial black hole. If please you have questions, please interrupt me. So that's the standard zero-order metric, where at super horizon scale, we have an very nice property for cosmological perturbation. Independently of the amplitude of the cosmological perturbation, if we are talking about adiabatic perturbations, the curvature term, which describes them in the metric, is time independent. And this is completely general, does not depend on the amplitude. And so what I'm writing here, this is called the asymptotic form, or the zero-order form of the metric, where you see there is this k, which in FRW is constant, while now I put a profile. But you can also write this like an exponential. So basically, it's a perturbation. It's a radial perturbation of the scale factor in a certain sense. So you are perturbing the scale factor because of now it's not homogeneous. You decouple. You have the standard time scale factor, which is related to the background evolving, and then you have a geometrical term which tells you how your scale factor is perturbed locally. And this geometrical term is time at super horizon scale is time independent. That's the nice property. You have this nice decoupling. And then what you can do, because perturbation form when the value of zeta is order 1, because otherwise you cannot form primordial black hole. You cannot approximate this because in cosmological perturbation theory you write e to chu zeta like 1 plus chu zeta. And then you find yourself in the standard theory of linear cosmological perturbation. But then you cannot do that because this is order 1 for primordial black hole formation. So you have to stick with this exponential. So what you can do, is to do perturbation theory in terms of the gradients. So the delta are not small, but what is small at super horizon scale, the gradients are still small. And so you can do a perturbative expansion in terms of gradients. It's called gradient expansion, this technique. And it's an analytic technique that allows you to compute the initial conditions to use consistently, analytically, to set up your initial condition for your numerical simulation. In particular, you do this in all your quantities. So you do gradient expansion in all your Hydro plus GR equation that I showed you earlier. What I'm plotting here is just the solution for the density contrast, which is delta rho over rho background, where you have this nice 1 over AH, which is it's a self-similar growth factor because it is expanding the perturbation in this regime. And then this profile, depending just on the gradients of the curvature perturbation. And you recover the standard nabla squared zeta, coming from linear perturbation theory, plus this nabla zeta square, which, if zeta is very small, is much smaller than 1, this term is much smaller than this one, you can neglect it. And the exponential is going to be order 1, and you exactly get back in what you know from linear theory. But in this gradient expansion, you have to stick with both this term and this exponential. So you cannot go very easily to the Fourier space. If this would be neglected and this would be 1, nabla square in Fourier space become k square nabla zeta k, no? But this is not the case, so you have to stick with this nonlinear term, and so going to the Fourier space is more complicated. But the real collapse happens in real space. So what I'm saying is that for primordial black hole formation, the collapse happens in real space. So you have to analyze everything in real space. And then I'll show you what you can do to connect with the power spectrum defined in Fourier space. So after understanding, so this is how you set up the Nizza condition in gradient expansion. So basically, using this separation of variables due to super horizon scales, you, given your zeta, or your k, these are related to, they are the same thing written in a different coordinates. Given your zeta profile, your curvature profile, everything is given. In terms of GR, of general relativity, the curvature profile is embedded in the singularity. So this is the Russian school of physics. General relativity does not know anything about inflation or any theory producing the spectrum of perturbation that we observe. So we have to put that on top of general relativity. So in terms of general relativity, you have to specify by hand at time equals 0 in the singularity a spectrum of zeta. And then everything evolves. In practice, what you do, your cosmological model produces a power spectrum. And so there is a way, using Fourier connection between Fourier space and real space, to compute the spectrum and the typical profile of zeta from the power spectrum. But it's your inflation model or whatever you have to produce your power spectrum that will tell you what you have to put in this profile. General relativity will give you total freedom. So you have to choose it by hand in terms of GR. Is that what I was doing in the past? In the past, I was just choosing this by hand. Now, after some work done in the recent years, we have found the connection how to specify zeta in terms of the power spectrum. And so that gives you the link from your cosmological models to the result of the numerical simulation. So now we have the bridge. So the perturbation amplitude is defined in terms of, this is what is called the compaction function. So tells you the difference between the mass at a given radius and the mass of the background. So the compaction function in general as a typical for a single peak goes like that. Start from 0 for boundary condition, goes to a mass and then back to 0. So I measure the threshold at the peak of the compaction function because it's where the black hole is going to form the horizon. So the maximum of this is going to be, so the compaction function at super horizon scale is time dependent, like zeta is given by this quadratic combination of r zeta prime. And the nice things of this combination is that, so I measure the threshold at the peak of this when this is equal, the derivative of this is equal 0, I found where I have the peak, and I found the amplitude of this, and this the amplitude of my perturbation. But the nice things of this quadratic correction is that, in general, because of this nonlinear term, which is not negligible, if zeta is a Gaussian variable, in general, the density contrast is not a Gaussian variable, never. However, we can, because of this decomposition, if zeta is a Gaussian variable, r zeta prime is a Gaussian variable, and then I can write my delta like a Gaussian delta with a quadratic correction in terms of a Gaussian delta. So in other words, I want to use peak theory, which is a theory for Gaussian variables that tell me where I have a perfect control of my probability distribution, to compute to the abundance of primordial black hole. And to do it consistently, I make a decomposition of my perturbation delta, which is intrinsically nonlinearly non-Gaussian, in a Gaussian component plus a correction. And that's allowed me to still use peak theory. Anyway, this is just a simple, please.
There's a lot of stuff that goes into this.
Yes, a lot.
So you're assuming still ideal hydrodynamics?
What do you mean?
There's no, so where are the viscosities?
At the moment, I said a perfect fluid. P equal,
so you're assuming ideal hydro?
At the moment, yes. Of course, you can, in general, I mean, in the early universe, you expect that the perfect fluid is a good approximation.
But the density is fluctuating.
Yes, but the question of state is not depending on the fluctuation of the density. It depends just on the microphysics.
Okay. Okay. But I mean, and you expect that the perturbations due to, let's say, the temperature field fluctuation or the velocity field fluctuations are small compared to the density of the gravitational perturbation?
In radiation-dominated universe, I think is a good approximation. In another context, for example, in a matter-dominated universe, I don't think so. But
how do you know? I mean, it depends on the size of the viscosity. Like, how do you know what the viscosity
that's what I mean. We cannot go. We don't have a time machine to go back in the early universe to measure the viscosity. That's it's the typical assumption that we do to describe the history of the early universe, and that's what typically is. I think it's a good approximation.
So then with these perturbations, are the equations still hyperbolic? You can still solve them, or?
Yes, if for a perfect fluid they are hyperbolic.
Yeah, I mean, this is what I was going to also ask.
Of course, if you put a viscous term, they will become parabolic, but you would still be able to solve them. I mean, you will still be able to solve them. It's going to be more complicated, but then you will still be able to do. I mean, we solve a parabolic equation nowadays in the elliptic equation. We do that.
With what method?
Or finite differencing, or depends on the SPH. Depends. I use finite differencing. I mean, it's more complicated because if you are hyperbolic, the questions are more explicit. If they are parabolic, there are implicit terms, so you have to do a more implicit solution, and then it's numerically more elaborate. But we do it. Now computing machine is powerful, so we can do it. In spherical symmetry, we can do it for sure. Even in 3D, people do it. In magnetohydrodynamics, they do it. It takes a long months to run a single calculation, but we do it. Okay.
Yeah, sorry, by the way, so it's been 45 minutes, and I think at the latest at 12:10 we should leave.
12:50. Ah, we have to leave the room.
Because there's likely a class then at 12:15.
Okay. I'm very pedagogic, I'm sorry.
This is good, yeah.
Okay, anyway, very quickly, this is just saying that in this slide, what I'm showing you is that this is my work, where basically I show that how the threshold is vary in terms of the profile. So depending on the initial configuration of your compaction function, which is given by your curvature, if your compaction function is very broad, the pressure gradients are less effective, and so the threshold is close to a minimum value, which is 0.4, because we are in radiation. Instead, if you get with the compaction function is peaked and peaked because that's depending on the particular shape that you put for your zeta function, then the pressure gradients are more effective, and then the threshold is larger. Because typically what we understood is that all the physics of the collapse is embedded in the typical shape at the peak, where you will form the horizon. So broader is the peak, smaller is the threshold, because the pressure gradients are less effective. More peaked is the compaction function, larger is going to be the threshold, and more difficult is going to be primordial black hole. And all this can be parameterized with this shape parameter alpha, which is defined in terms of the second derivative of the compaction function over the height of the compaction function. Okay, well, this is just showing basically how the numerical results, which is of the threshold in terms of this alpha parameter behaves, and there is a fit that we found. I will not anyway. There is now a fit. Now we know. Now, if you know the typical shape, you can compute with this fit given in radiation of the universe at least, which is the threshold. And I mean that's peak theory, what I was mentioning before. So if you have a Gaussian distribution of your delta, which is this one, then you can compute the variance in terms of the power spectrum, and then you can compute the abundance of primordial black hole, where you see all the physics coming in. The threshold over the variance, the gamma factor from the critical collapse, and K star is the typical peak of the power spectrum. So in general, okay, and these are a bit technical, but the message of this is that if you have a Dirac delta power spectrum, you need to have, if you want to have all dark matter in primordial black hole just above Hawking evaporation, you need the peak of the power spectrum, which is order 1. Instead, if you have a very broad power spectrum like a top hat, because you have more power spread between more modes, you can have the same abundance of primordial black hole, so all dark matter in primordial black hole, with the peak of the power spectrum order 10 to the minus 3. So the information about the abundance of primordial black hole is embedded in two things: the height of the power spectrum and the width. These two parameters allow you, using peak theory, allows you to tell you exactly which is the abundance of primordial black hole. And with this prescription that we found, in this prescription we put together all this physics, both peak theory and numerical simulation together. You start from the power spectrum. You solve two integral equations, nonlinear with Mathematica, and with this fit, and then basically you start from the Fourier space, from the power spectrum, and in the end you get to the typical threshold. So now that's really the link. So peak theory together with numerical simulation give you a perfect matching, understanding how to, from the very beginning, from your cosmological model coming out from inflation, to compute everything up to the parameter that you compute with the numerical simulation of a single collapse. So up to the first 3 passages, it's a complete independent of the question of state. The last fit, the value of the question of state, of course, is important. This fit will, of course, be different. So in other words, we are basically, with this prescription, we are computing the typical curvature profile given the shape of the power spectrum. That's the message. And so you can see here, for example, for a log normal power spectrum, how the threshold behaves in terms of this big delta is the typical parameter of this log normal power spectrum that gives you the threshold. So for a broader power spectrum, the threshold is smaller. For a more peaked power spectrum, the threshold is larger, basically. So the typical shape of the power spectrum is related to the typical shape of the compaction function in a one-to-one connection with some non-linearities in between. But physically, that's it. Okay, let me skip this. Now, this is a bit technical. Let me just mention one thing. All this seems very nice and complete. It seems that from what I told you that you understand everything. Not yet. In the sense that all this, there is some assumption that at the moment, because when you apply peak theory, you are doing this at super horizon scale, at initial condition. But primordial black hole form later after horizon crossing. So there is an hidden assumption in all this, is that we have a perfect control from what happens between the threshold and the variance computed at super horizon, actually at super horizon linearly extrapolated at horizon crossing, but then all the nonlinear effects during the collapse, we don't know what happens. So we don't know what is the effect on the statistics because of the nonlinear effects inside the horizon when everything is collapsing. So this is still some work to be done here to understand that. In other words, we need to know what is the nonlinear transfer function, because at the moment the variance in peak theory is computed using the linear transfer function, which we know. If we would have the information of the nonlinear transfer function, then we would be able to know everything. And that's what I'm trying to understand with one of my colleagues, from the numerical simulation, doing lots of them to extract this information, at least at second order. Okay, this is about self-similar solution, which is a bit technical. I will skip it because I want to tell you at least something about the signals that you potentially get from primordial black hole formed during the QCD. Then they emerge emitting gravitational waves. So primordial black hole formation is this overdensity collapse forming, but later on with the universe, you can have binary system forming. They accrete and merge at some point, emitting gravitational waves, and then we might observe them nowadays. So that's, after lots of numerical simulation done in Rome a few years ago, that's how the threshold changes because of the softening of the equation of state. So this is the equation of state in terms now of the mass of the horizon normalized to the solar mass. So this is basically telling you in terms of mass scale when the perturbation is crossing the horizon. So depending on if it's crossing the horizon earlier or later, the threshold is different. Typically, there is a 10% softening. And this 10% softening gives, because if you remember in peak, maybe you don't remember, but in peak theory, the abundance of primordial black hole goes like E2 minus delta C over the variance square. So a 10% in this quantity, it's a huge change in this exponential square. In fact, this 10% produce a change of 3 orders of magnitude. So this softening naturally increased the possibility of primordial black hole formation of 3 orders of magnitude more because of this large sensitivity. And then, of course, there is also a modification now because there is an intrinsic scale. The critical collapse is not anymore precise, but is perturbed. So depending when you cross the horizon, you have this is before the minimum, this is after the minimum. So you have to take into effect modification of the scaling law, taking into account all the different moments of the horizon crossing during the equation of state. So there is basically a perturbed scaling law, where now all these are scale-dependent parameters. And if you include all this, you have that's basically, let me go to this plot, which is the more meaningful. This is the typical mass distribution for primordial black hole formed during the QCD. You see, around 2 solar masses, where you have the minimum of the equation of state, you have a peak in mass distribution. And because it works like an attractor solution, changing the shape of the power spectrum does not give any significant effect. So it's changing the shape of the initial configuration. What has an effect, of course, is the spectral index, what is called DNS. I don't know if the spectral index of power spectrum, of course, will is called the tilt, and will tell you if you have more effect coming from the blue tilt on the red tilt. And so, but nevertheless, the peak is very robust. So change just the tails, the DNS of the power spectrum, but it's not playing any role on the peak, which is very good, because basically it's quite solid, the result, quite independent. The peak is completely independent on the inflation model. Finish with this.
As predicted.
I'm sorry, I was not. So that's what, and if you now make a Bayesian inference analysis, and you ask yourself, what's the possible contribution of primordial black hole to LVK gravitational waves? What we have here in this plot, 3 channels of possible black hole formation. Sorry, 2 channels of black holes, astrophysical black hole and primordial black hole, and 1 channel for neutron stars. This is the neutron star range. This is the astrophysical black hole range. And primordial black hole, they go in all the range. So the message, these are basically the number of events plotted as function of the primary mass. And basically what this plot is telling you that there is a potentially subpopulation of primordial black hole contributing to the emission gravitational waves, which is not affecting significantly the neutron star and astrophysical black hole range, but they don't, because primordial black hole do not suffer of the lower mass gap. There are, in fact, this is the result from the Bayesian inference analysis. There are few events already in the catalog, these 3, where they have a not negligible probability to be a primordial origin. And it's not a surprise that one of the 2 components falls in the lowest mass gap. So the message of this is that explaining primordial, all this LVK signal with primordial black hole is almost impossible, because this is done in a very agnostic way. We don't push primordial black hole to be the solution. We just give 3 possible channels of formation: neutron stars, astrophysical black holes, primordial black hole, and we ask the Bayesian inference analysis to tell us what is the possibility. And it tells that mostly they are astrophysical origin, but some of them, potentially, they are really primordial black hole. And in the future, we will know, because if this is the case, we expect in the next 04 and 05 run to have a certain number of subsolar events that we should observe. So this claim is going to be potentially falsified or proved in the next year. At the moment, and then I finish, the formation of primordial black hole during the QCD is compatible with the constraint and contribute to about 0.1% of the whole dark matter up to. So if you want to explain dark matter, you have to use the asteroidal mass range where there are no constraints. The QCD range gives a small contribution, which nevertheless is still, it's a possible explanation for LVK mergers. And then I'll leave you with my conclusions. Thank you.